subproblems and the order. Okay, so what is the optimum substructure property, right? Suppose this is the longest common subsequence. I don't know whether it is. So then what? This A corresponds to maybe this A and this A. Then what? Then what can you say? What is the optimum substructure property? That this is what? Okay, get back. Okay, we're going to wrap up today with more standard dynamic programming examples on. So you can hear me and see everything, right? Okay, so the problem we want to look at is the longest common subsequence of two strings. You're given two strings A and B like this over some finite alphabet. In this case, the alphabet is A, B, C, but in general, some finite alphabet. And we want to find a subsequence of these two strings, which is common to both strings and is the longest. So one such common sequence is I've written down here, and obtained by these underlined characters in both the strings. So I don't know whether this is the longest, and we want to find in general, given two strings A and B, we want to find the longest common subsequence using dynamic programming. So if I want to use dynamic programming, here are some of the points we need to look at. Identify some optimum substructure property, then write opt solution as some sort of a recursive equation, and then identify the subproblems and the order in which you want to compute, and typically you will compute it in a bottom-up fashion from solution to very small problems, and we build up to our final solution. You have to live with it. So what is optimum substructure property? We said, suppose that here are these two characters that are matching, and that corresponds to A. Then what I need to find is the longest common subsequence of this string and this string, right? Because if there is even a longer substring than this, then I could replace this by that and I get a longer subsequence. Okay, so and here I've been also emphasizing some choice we will make that will determine this optimal substructure, right? Okay, so what, how do we want to start? So in particular, if yeah, look at the last characters. So let's say my A is A1, A2, sorry, were you saying something? I couldn't hear. Okay, and I heard you, but the voice was very feeble. Yeah, I understood. Yeah, just a minute. Yeah, they want you to zoom in on this side of the board first and then move the board arm. So zoom both. Okay. Is that okay? Is that fine? Okay. So my B is B1, B2, Bn. Then here's the, let's say I'm looking for the longest common subsequence length of A1 to M to B1 to N. Then if AM is equal to Bn, then you better take it, right. Without loss of generality, you can say the optimum will contain these two characters, because if it does not, you can add it, right. Then LCS of, let's say, AM Bn. So I'm going to call this, to make life simpler, AM Bn, but what I mean is 1 to M, right. This is actually 1 to M, is I get one character by the last characters, plus now you compute the LCS of A M minus 1 comma B n minus 1. They don't match like here, then yes, then you know that clearly this character and one of this is not there in your optimum solution. I mean, the character may be there, but that particular location is not in your solution. So you just omit this and find the maximum. So you can verify that. Else LCS of AM Bn is equal to LCS of A M minus 1 Bn. That is, you go up to find the longest common subsequence of up to this point and this whole thing, or match this with this. So whichever is maximum, you are going to pick this. So pick the max. That's it, right. So this is, I've written optimum solution as a recursive equation. Now what are the subproblems I need to compute? The subproblem is to compute the longest common subsequence of some strings. What are the kind of substrings I have to compute? Well, if you look at the recursive thing, it tells you that I have to compute 1 to something and 1 to something, right. This is 1 to M minus 1, 1 to N, 1 to M and 1 to N minus 1. So in general, 1 to something and 1 to something in A, 1 to something in B, and find the longest common subsequence. So the subproblems are A I and B j, right. What this is 1 to I and this is 1 to j, and the recursive formulation would be 1 plus LCS of A I minus 1 B j minus. So exactly this, instead of M and N, you can replace it by some intermediate if A I equal to B j, or min of some appropriate thing here otherwise. So you get the subproblems. What is the order in which you are going to compute this? Oh, sorry, max. Yeah. This one. Okay, so the order in which you will compute is just go from 1, 1, 1, 1, 2, 1, 3, 1, 4, and in this increasing order basically. and eventually you will get to AMN. So, the proof of correctness lies in proving this, right? This requires and the way you prove it is look at the optimum solution, look at the last characters and see where they are going, and then you realize that whatever else is the optimum solution for one of these two things. Okay, so I'm not going to prove this, but this requires case by case. Yes, if they match, what happens? If they don't match, what happens? Yeah. And so this is it, right? I mean, this is the template we are just following, and now you convert it into a loop. Find the running time. How many entries are you computing, and how much time does it take? The number of entries you compute is for different values of I and different values of j. Right? So, it's m times n. You have m choices here and n choices here, and for each entry to compute this, you just have to look at the last entry, and if it is the case, you are done. If it is not matching, then these two entries are already computed, so you just have to pull out from there and pick the max. So, constant time, so order mn. Okay, let's look at. So here the choices are not so much. We look at examples where there are exponential number of choices, but dynamic program, the optimum substructure property brings down the number of choices, right? We have seen examples, traveling salesman problem, coloring, and set cover, various problems. We have seen already where we can bring down the number of choices by using the optimum substructure property. Okay, so this is matrix chain multiplication. So, I have removed the template, but you know the template now. So, what is the problem here? You are given a bunch of matrices and you want to multiply them all together. Okay, how many of you have seen this problem? Okay, almost all of you here. Okay, so the problem you want to do is the following. So each mi is a n1 by n2 dimension. This matrix is an n2 by n3 dimension. Let's say k. No, in k by nk plus 1. Okay. And the goal. I will give an example to illustrate what it is. So, compute the minimum number of multiplications required, the scalar multiplication Okay, what do I mean by here? Let's say you have matrix M1, M2, M3, and this is of dimension 5 by 100, this is 100 by 80, and this is 80 by, okay. Matrix multiplication is associative, right? So, there are many ways to my goal is to compute the product M1 into M2 into M3, okay. Since matrix multiplication is associative, I can compute M1 into M2 first, and then multiply by M3, or I can compute M2 into M3 first and then multiply M1 with that product. And each of these two choices give me different kind of scalar multiplication. So, if I do M1, M2 into M3, how many multiplications do I do? M1 into M2 takes 5 into 100 into 80. So, that is 40. Let us say I use a standard high school multiplication. I am not doing anything fancy, no Strassen kind of multiplications. So, it is 5 into 40 and 1. Oh, just 40,000, right? No, plus I will come to. First, I want to, 40 and only 4,000, right? No, 40,000. Okay. It's 5 into 100 into 80. That's the number of, because you want to multiply a matrix which is of dimension P times Q and another matrix which is of dimension Q times R. The standard high school multiplication will take P into Q into R multiplications, right, to get the final matrix is of dimension P times R. So, there are PR entries you are computing, and to compute each entry you will spend Q multiplications. So, it is PR into Q multiplications you will do. So, to do M1 into M2 you will do 40,000 multiplications, and then the product matrix is of dimension 5 by 80, which you are going to multiply by this. So, that is 5 into 80 into 20, which is okay. Is that good? Okay, I am going to believe you. So, if I do M1, M2 first and then do M3, the total number of multiplications I will do to get that is 48,000. Is that clear? Yeah? Yes? No? Okay. Now, suppose I do M2, M3 first. How many multiplications that is? I have a calculator sitting here. Huh? 16,000. Okay. And my dimension would be 100 into 20. So, now 5 into 100 into 20 is this, that will be 10,000. So, that is 26,000. So, as you can see that even for just multiplying 3 matrices, do I have any more choice? There are 2 choices here, right? Any more choices? Okay, no. So, I have 2 choices and each one gives me a different kind of total number of multiplications. Okay, how many choices are there in general? Catalan number, right? I don't know that everybody sees this. So, the number of ways of, it's exactly the number of balanced parentheses. It comes up in multiple different places in discrete math. So, number of ways, if I have k different multiplications, I can do M1, M2 first, and then I do M3, M4, and then I can do this, and then, so there are many choices. The actual number of choices is, you can write a recurrence and solve it, and the number of, actually we will do write a recurrence, and that would be about roughly 4 power k. It's the Catalan number. So, number of choices 4 power k by something, k plus 1. So, among all these choices, I want to compute the one that gives me the smallest number of total number of multiplications. Okay. So, this is the problem. So, clearly I do not want to go through all possible choices and count it, because that is exponential in the input size. So, this is the In fact, good exercise for you guys who have seen this problem is try and show that, okay, what would be a greedy approach to this? What would be a greedy way of doing this, right? No, no. No, there's nothing to do with ordering. So suppose I have, here is a matrix which has some dimension 1000, and then the next matrix is 1000 by 2, right? This may be 10 by 1000 or something, and then there is 10 by 50. So there are these matrices, right? The greedy choice would be to nuke this out quickly, because if you keep the 1000 alive, right, then when I am going to multiply these two matrices, I will have a multiplication by 1000, and the dimension would be 50 by 1000, and then I multiply by the next other matrix, the 1000 will survive, it keep on survive. So do this multiplication quickly, so that the dimension will become 10 by 2, this big number goes away. So this is one greedy choice. We take the largest dimension and somehow make it go away by doing that adjacent multiplication, and then keep going, right? One can come up with many other choices of greedy and try and show that such greedy approaches do not necessarily give you the optimum solution. Okay, that's a very good exercise. Come up with examples where this kind of obvious greedy choice doesn't really work. Okay, so I mean, greedy and dynamic programming are somewhat related, right? So the problem with dynamic programming is that the approach to dynamic programming is that we don't give up on any choice. We are actually going to do doing exhaustive, but in a more carefully systematic way by storing solutions to subproblem. Greedy makes some locally greedy choice, right, and it doesn't run through all possible choices. So that's a pitfall. Sometimes it works, sometimes it doesn't. Okay, so if I want to use dynamic programming, start with some choice and then recursive substructure, and then everything falls in place, right? So what is the choice you want to make? So in general, my matrix looks like this. Okay, so the dimensions are n1 by n2, n2 by n3, and so on. I want to exhaustively really try all possible things, but that's like 4 power k choices. But I have this optimum substructure property. Let's see whether it is there. How is it there? First, how do I break up my problem recursively, find the optimum substructure property, and then we'll be in shape. So what should I do? What is it? Okay. So look at the last multiplication you're going to do, right? So what will any optimum algorithm, an algorithm which optimizes the number of scalar multiplications will perform something, right? It will perform some multiplications. It has computed some big product. Then finally, it will multiply A and B to get my final chain, matrix chain, right? The product of the matrix chain. I mean, this could even be something like, or B could be just one matrix, the last matrix maybe. This is MK. Maybe it figured out that this is, I'll do this and then multiply by MK, whatever, right? So in general, it makes the last multiplication, some product it has computed, some other product is computed, then it's doing the last multiplication. So what is the optimum substructure property? That these two must be optimum. So somehow it decided that I am going to do the last multiplication, this and into this, then the way I would have obtained A multiplying these chain of matrices must be an optimal way, which minimizes the number of multiplications to multiply this matrix, right. So, let us say some M1 to ML and then ML plus 1 to MK. It should not, I mean, again it follows from this cut and paste argument. Suppose it did not use the best way to multiply these matrices, replace it and use the best way to multiply, and then replace this and use the best way to multiply these matrices, and you will get overall fewer number of scalar multiplications, because the final dimension, what is the dimension of matrix A? It will be n1 by nl plus 1. The dimension of the matrix this would be nl plus 1 times nk, right. So, k plus 1. Okay. So, whatever way you multiply M1 to ML, there is some number of multiplications you have already spent. Similarly, some number of multiplications you spent here, and you add N1 into NL plus 1 into NK plus 1, that is the number of multiplications to do this product A times B. That will be your total number of multiplications. So, you better do this optimally and this optimally, right. That is what. So, now your problem, the sub problems are, I want to multiply 1 to k. Well, I do not know L, right, but we have been through this, try all possible choices and pick the one which minimizes the value. So, the problem 1 to k now breaks it into 1 to L and L plus 1 to k for various values of L. Okay. And I think we had this in some scheduling problem or some other problem. So, this RNA sequence problem, where this is not of the 1 to k problem, right. This is 1 to something, but this is not 1 to something. So, what are my sub problems? The sub problems would be some I to j, right. So, it is number of multiplications required to compute minimum number of multiplications required to compute mi plus 1 to mj for some arbitrary I and j intervals. So, we made this choice, which is the last choice determined my sub problems. So, what is the order in which I will do? Compute. So, I have to compute this, that is it, right. I have to compute this for various values of I and j. In particular, when I is 1 and j is k is my final goal, final output, and I just build it up. What is the order in which I am doing? So, what is smaller in my recursive thing? The gap I minus or j minus I is decreasing, right. For 1 to k, I cut it at some place and then I have this and this, these are smaller intervals. So, do it from smaller, the increasing lengths of j minus I. The starting point would be when j minus I is 1, right. The base case would be I have two matrices I want to multiply, I know how much time it takes exactly, right. The best way to multiply, there is only one way to multiply, you take the product. This is the base case, and then you build gradually in this increasing value of the difference j minus I. Eventually, the j minus y difference will reach k. How much time does it take? Oh, so finally, what is the recursive formulation? Mij would be best way to multiply I to j would be minimum of various values of L, the place to cut, M IL plus ML plus 1 J plus, yes, this thing, right, whatever, which would be Ni times NL plus 1 times or Nj plus 1. Run it over all possible values of L ranging from I plus 1 all the way to J minus 1. So, this is a constant time computation if you have computed these smaller problems, because, no, not constant time, because you are running over all possible values of L. There are, up to J minus I values possible. So, overall this would be like an n cubed algorithm, okay. N square entries. Okay. And again, I am not, finally this tells you what is the number of multiplications, but if we really want to know the order in which you need to multiply, you need to store this L values, that is it. Okay. So, for those of you who have seen this problem, the exercise would be to try some greedy heuristics and argue, come up with examples where it does not work. Another very similar kind of problem also has a Catalan number in the number of choices, is this optimum binary search tree problem. How many of you have seen this? None, really. Okay. This is interesting because it's also somewhat related to the splaying you have already seen. So, what is the problem? So, you are given a set of characters, some strings, numbers, whatever, some set of objects. So, let us call this S, K1, K2, some Km keys, where it's a static problem. So, everything is given to you in advance. Okay. So, organize S in a binary search tree so that this is an easy problem. You have all seen this, you know how to do this, right. So, I give you some M keys and I tell you, okay, organize them in a binary search tree. I tell you this is the data structure I want you to store it, and I want to minimize the search time for any of the keys, worst case time, right. So, how would you organize it? Right. So, what would be the root? Median. It is a static problem, I give you in advance. Okay. Yeah, you can solve it. It's all pre-processing is allowed. It's a static problem. If it is dynamic, then you may want to think in terms of red black trees or ABL trees or something, right? It's static, everything is given. So, take the median element, put it as a root, create a nicely balanced binary search tree, and you know that log m would be the worst case time to search any key, right. So, now the twist of this problem is that I also give you some probabilities of searching for these keys. Okay. So, imagine these are some English words or something, and not every word will be searched equally likely. Okay. So, I also have probability P1, P2 up to Pm. Think of it as a probability or frequency, which is probability of searching Ki, which means that I am not, first of all, I am not interested in worst case, expected, right. I am interested in so I give this set of keys and I am going to tell you that I am going to search K1 50 times, K2 23 times, K3 17 times, Km once or something like that. Okay. So, now the problem is different, right. Now, I am telling you total number of searches I am going to do. I am going to search K1 50 times, K2 so many times, K3 so many times, and maybe I have totally 100 searches distributed in this fashion. Now, organize your search tree, organize it in binary search tree, so that the time for the total cost is minimum. Okay. So, let us say I have this characters A, B, C and A less than B less than C, and maybe I will tell you that I am going to search A 25 times, C this is my frequency. Think of it as a probability, think of it as frequency, does not matter, right. So, if you want probability, you make it, this is 80%, 18%, 2%. This is my frequency. I am telling you I am going to do 100 searches where A is going to be searched 80 times, B 18 times and C twice, right. So, now let us, there are multiple different binary search trees possible. So, I could put A here and then B and then C. If I do that, what would be the cost of search? Suppose I know the cost would be the length number of comparisons I am doing. Okay. So, the total cost on this search tree would be, so for 80 searches I am spending only one cost, for 18 I am spending 2, so that is 36, and for 2 of them I am spending 3. So, that is my cost. So, that is 122 whatever the units is. But if I do, then it will be for 80 searches I am spending 2. So, that is 160, 80 into 2 plus 2 into 2. So, that is like 4, and then for 18 I am spending 1. So, that is 172. Okay. I can also, just to not to exclude anybody, I can write this tree and see the expected cost, and that is going to be even bad because A is going to be down. Okay. You can also add more probabilities. The probability I might also search for somebody less than K1. Okay. So, Q0, Q1, Q2 and Qm is, so Qi key between pi and pi plus 1. So, the most general version of the problem, you are given a set of keys, probability of searching them, probability of searching their gaps, okay. And you can still, same thing, right. I have some probabilities here. So, number of times I am going to hit here would be again the number of comparisons I am going to spend, okay. And you can take the cost, and I want to do the best average cost overall. What is this tree that minimizes the total cost? Okay. You can again come up with some greedy heuristic, right. What would be the greedy thing? Pick the largest frequency element and put it at the root, okay. It doesn't necessarily give you, because I could make all the frequencies to be 0 and put a very high on the gap, or various other examples, right. So greedy would be put largest frequency element at the root and then recurs, right. So exercise would be to show give examples where this is not optimal. Hmm? 654, is it here? Okay. Well, come with, put in some gap probabilities also and come with examples, and you can see some. Oh, it's the same thing, right? So, how many times I am going to hit here times the length of this path is the number of comparisons I am going to spend, right. So, imagine my search, I am giving you x1 number or p1 number of times I am going to search here, p2 here, p3 here, q1 here, q2 here, whatever and all that. So, you multiply that frequency by the amount of time you are going to spend, which is same as the number of comparisons you do to get there. Again, how many choices do I have? Catalan number again, because you pick a root and then there are so many choices for the remaining thing. So, what would be a recurrence? So, let me erase this. Number of BSTs. This is the same as the number of ways of parenthesizing the matrices and so on, the same recurrence. So, what would be the recurrence? So, suppose I pick, let us say the keys are k1, k2, km, right? Yeah. So, I pick ki as the root, then you have t of I minus 1, right, t of I minus 1, number of trees on I minus 1 keys plus t of n minus I, number of trees on the remaining n minus I. And what is I? Yes. So, what should I do here? Sum, right, because for every such I, so I would be 1, 2, n, n, because I is the root. So, that is the number of choice, and the solution to this recurrence is the Catalan number. Okay. So, it has the, oh, you are right, thank you, yes, it is t I minus 1 times t of n minus I, right. So many choices, for each such choice there are so many different choices, right. So, this is the exponential number of choices. So, yes, so it's you don't want to run through all possible choices, but very simple dynamic programming, right? Absolutely simple. What do? What is the choice you have to make? Choose a route, right? Once you choose a route, you don't want to try all possible binary search trees on the left. You just pick the best optimum binary search tree, which, because the good thing is that once you choose your I, 1 to I minus 1 are contiguous sitting here. So, all the gaps, k, P1 to Pi minus 1 and the gaps, they are all here. So, take those, compute the best tree, and similarly compute the best tree on the right hand side, run over all possible choices, and you get the optimum. So, that is it, right. So, what are the sub problems? Right. 1 to I minus, it's very similar to the matrix multiplication, the RNA sequence thing, where we have 1 to I minus 1 and then I plus 1 to n. So, in general, the sub problems would be the sub problems let us say Tij best binary search tree, best meaning that minimizes this expected cost for ki plus 1 up to kj, all possible values of ij. Then we know what or the cost. Then what is the recurrence? Tij is equal to minimum over some k, let us use some root r, and r has possibilities of I all the way up to j. So, once I pick r as the root, then I look at 1 to r minus 1, right, 1 comma r minus 1. Okay. I might have an empty tree, I need to deal with it. Let us see, because if r is I, 1 to r, sorry, yeah, I to r minus 1, right. So, I to I minus 1, what does that mean? We will come to that, but stay with me for a moment. Plus T of r plus 1 to j plus what? Let us understand what is going on here. So, what is the cost? I said cost of a fixed tree would be summation Pi into level of I, right. The root is at level 1. Plus summation Qi into again Qj into level of j, or level j minus 1, actually it does not matter, right. So, I have a tree, let us say this is the gap node. If this is at level 1, 2, 3, 4, then the cost would be Qj into 1, 2, 3, because I do these 3 comparisons and I notice that this is a nil pointer. So, I don't make any more comparisons. So, number of comparisons is, if it is at level 4, then I do 3 comparisons, and if it is a successful thing, then I 1, 2, 3. So, that is the level. So, this is my cost. Given any fixed tree, what is the cost of the expected cost of the tree? We wrote down, right? We wrote down that example and I did the cost analysis. Only thing is I didn't write the gap frequencies, but it's essentially the same thing. Right? So, now if I choose R as my root, then I have a tree which is for 1 to R minus 1, best tree for 1 to R minus 1. This is the best tree for R plus 1 to J, sorry, I to R minus 1. Okay. So, there is a cost which is this kind of a measure. For this tree, there is a cost for this kind of a thing. What more should I add for the cost of the tree? So, this is the optimum cost for I to R minus 1. This is the optimum cost for R plus 1 to J. What more should I add? For the root, how much? PR. P is a success thing, right? Plus some more, I will come to that. But PR, right? Because this is exactly how many times I am going to search R is PR times, and there is a cost of 1 for that. So, PR into 1, that is a cost for you, right? Because this did not include R, this did not include R. So, I have to do that plus what? There's some more. Right. So, what happens? So, for every node here and every gap here, now their distances increases by 1 from what it was, right. Similarly, for every node here and for every gap here, their distances increases by 1, because when I computed the optimum cost, it is a cost in this tree, but in this big tree, every node's distance is increased by 1, right. So, if it be, so it's just summation pi, that's it, plus qi, summation pi plus qi, right, summation so if you include, this is 1 to R minus 1 or plus similarly the right, the whole thing, it turns out if you include PR also, it is the sum of all successful and unsuccessful gaps in frequencies in I to J. So, this would be simply, let us write this as weight of Ij, and what is this? This is, so the gaps starts from Qi minus 1. So, summation L equal to I to J Pi plus summation L equal to I minus 1 to J Qi. But the good thing is it depends only on I and J. I can compute this, pre-compute them and store them. Okay, it's just a function of the probabilities given. It doesn't depend on OR. That's all I want to say. Right? It doesn't. That's a beauty here. It doesn't. This quantity doesn't depend on OR. Right. So it's a recursive thing in the truest sense, that it's whatever the optimum here plus the whatever optimum here plus some fixed quantity which is the number depends on I and J. So, you find the minimum among them. That is it. Okay. So, that is it. So, that is you make the choice about the root, everything else falls in place. Only thing is at the intermediate stage, what is it you are computing? There is a little extra thing you need to pay attention and carefully, right. Similar, I mean, we did this in the matrix multiplication also, right. There is a cost for this plus something else, right. There was this product. So, similarly, it's a cost for this plus something, because everybody's depth has now increased by 1 because of this R. So, you adjust the cost of this to account for that. That turns out to be a good number, just depends only on I and J, it does not depend on R. I mean, not that it matters anyway. So for the overall running time. So how many entries are we computing? Our number of table entries is something like n square, because various I and j, and computing each one takes running over the gap. So it's time per entry. I mean, if you want to compute ij, it will be like j minus I, right? So in the worst case, it's order n. So this is overall an n cubed algorithm. Now the comment about splay trees is that, so here it's a static problem. I have to know the frequencies in advance. Then I can compute this best tree that minimizes the expected cost. It turns out splay trees somehow dynamically rearranges in a way that it actually achieves the best expected cost, right? So I don't know the frequencies in advance, right? So I have this keys, and suppose I am doing certain number of searches into x1, certain number of searches in x2, certain number x3, and so on. I don't know these numbers, but at the end of it, I take stock and say how many times I've done x1, how many times x2, and so on, and look at this best expected cost. Splay trees dynamically achieve that. That's the, so they achieve as good as the static optimal binary search tree, and there is a conjecture that there is this dynamic optimality conjecture which says that, so this is static, right? Suppose I allow reorganization of the trees based on what are the future requests, then compared to any dynamic reorganizational scheme, splay trees are as good as the best. Okay, that's a conjecture unresolved. But the nice thing about splay trees is magically they achieve this best tree which minimizes the overall cost even without knowing these frequencies. Okay, so I will wrap up by talking about all pair shortest paths, right? I'm sure again you've seen this, but don't want to miss them. Very interesting dynamic programming again. So you're given, you want a directed graph? Yeah, okay, fine. I mean, this is one example where adjacency matrix is as good. It's actually it is useful rather than an adjacency list. Okay. So you're given a directed graph with distances on the edges. These distances can be negative, but no negative weight cycle. And what do we want to find? Find the shortest path between every pair of vertices. We know how to find the shortest path from a single vertex to everybody else, right? This is what algorithm? Dijkstra's algorithm. If there are no negative edge weights, okay. This is very crucial. Dijkstra's algorithm assumes that there are no negative edge weights. Okay. If you have negative edge weights, you need what's called Bellman-Ford algorithm. Both these algorithms, depending on whether you have negative edge weights or not, given a vertex S is a single source shortest path, right? I can find the length of the shortest path from S to every other vertex in whatever time. And can I apply that to do this all pair shortest path? So, these algorithms, Bellman-Ford or Dijkstra, will be able to find the shortest paths, the lengths from a fixed source to everybody else. Now, I want to find the shortest path between every pair of vertices. So, what can I do? Yeah, just make S as try every possible vertex, and from that vertex to everybody else you can apply. So, apply this Dijkstra's are Bellman-Ford n times independently for every starting point, you will get all pair shortest paths, correct. So, but we want to do something better. If edge weights are non-negative, or Bellman-Ford starting at every vertex, so this Bellman-Ford, if you apply, it will be like an n to the 4. No, sorry, it's n square m. Bellman-Ford is nm, and you are applying it n times, so that's like an n square m. Dijkstra's will be slightly faster, n times m plus n log n. But it seems like an overkill that you are just applying this from every vertex without using the fact that there is some enough structure in when you find from one vertex to everybody else, there is so much hidden there you should be able to make use of, right. So, that is what dynamic programming helps. So, okay, so there are again let us see two different versions of dynamic programming. So, one is so what is the optimum substructure property? If we want to find the shortest path from S to T, then for every intermediate vertex there, this path is the shortest path. If not, I can remove it and put a shorter path, and I will get overall better ST path, right. So, that is what I want to make use of. So, in particular, the shortest path from S to T would be if I is an intermediate vertex. Let us write this length of this path from S to T would be, so this is sort of a recursive formulation, we need to build it from here. What are the subproblems? So, what is I mean there must be some progress. I mean, this must be a smaller problem in some sense, right, then only you can build it up, right. In some sense this must be a smaller problem. So, that tells you, so in what sense it is a smaller problem I want to think about, right. Because you don't want to write it stay in the same domain, because as such from S to T looks like S to I. S to I is also another one of those things. So, what is smaller about it? length is smaller, right? Okay, good. So now that gives you a starting point, right? So this is a smaller length. So let's define our subproblems like this. So distance from I to j using length m. Right? The shortest distance from I to j using at most m edges. So what is smaller? It's the length of this is smaller. Okay. That immediately suggests you this kind of a subproblem. Now you're done. Right? Dynamic programming is all about coming up with this and then apply your template. There is a base case with a recursion loop, complete it, right? So what is a base case? So one important thing is, since there are no negative weight cycle, the reason we assume this is that every shortest path is a simple path, right? See, if you have a negative weight cycle, then I can go from I, go to a cycle which is of total negative weight. I can keep going through it, I will get my distance comes down, right? Since I do not have a negative weight cycle, then every path is of length at most. It's a simple path, so it's of length at most n minus 1, because there are no cycles. So that tells you the highest m I should try is n minus 1. There is a limit to it, right? So my goal is d n minus 1 ij, as the shortest paths are simple paths, right? No cycle. What is the base case? There is only one edge. This would be the distance ij, whatever the distance is. Okay. So if edge is not there, let's assume the distance is infinity. Okay. So if I'm allowed to use only one edge, I just have to go direct edge for every I and j, and otherwise if there is no such edge, that will be infinity. And what would be the recursive step? Would be ij, right? Possibly, maybe I don't even need m edges. If you allow me to use more edges, I may not necessarily get the shortest path. So test, maybe the m minus 1 edges itself is the shortest path using it, because it's at most, right? I'm not insisting that you should use m edges. Or, yeah, okay, so it's a min of two quantities. Or I to some k plus dkj. What is k? Min over all possible k, right? Yes, right. So the shortest path using m edges, whatever that m, the previous vertex is some k, and you don't know that k, run over all possible choices. Aha. Yes. Good. We'll okay. Okay. let's complete this and then we'll come back to your optimization. So now this is it, right? I have a base case, I know where I want to go, and I know how to proceed in an incremental step, and let's now compute the overall time. Right. Finally, I want to go from D1 and then I come D2, D3, and finally I get to Dn minus 1. And so what you are saying is that why do I want to go from Dm minus 1 and then add 1? Very good observation. We'll make that observation and get an improved algorithm, but let's understand the running time of this algorithm. How many entries? Totally, how many entries are we computing? Remember, this is for every ij, n, right? So it's n cubed, correct? N cubed entries, right? So n choices for I, j, and m. This m as well, because we know n meaning n minus 1, whatever. So it's basically theta n choices. So it's n cube entries, and to compute each entry, how much time? Min over all k, which are neighbors of j, it could be as bad as n. So it's overall n power 4. Okay. So now Ramesh's observation is that why do I want to go from, why not jump? So what is a natural way to jump? So why do I go to, I mean, I'm computing, think of this whole matrix, I'm computing as dm, right? This is, my final goal is dn minus 1 matrix. And I'm computing d1, d2, d3, d4, and incrementally going to dn. Do I really have to go incrementally? What is a better way to do? I want a path of length at most n minus 1. In particular, here you just gave away and you are using only 1, right? So why don't I use m by 2 and m by 2 here? I will go from I to k using at most. So you pick the previous vertex. Why not pick the middle vertex in that thing? And then there is a path of length at most m by 2 from I to k, and a path of length m by 2 from k to j. Right? Then I don't need m minus 1 to go to m. I can keep doubling. So what would be the running time?